a logical operator here that is already defined by the structure of AME state, and then you concatenate, and this is how they spread to the boundary. By this procedure, you already know how also stabilizers are defined on the boundary, so you can use them to change the positions of logical operators such that they mimic the fact that you can have this encoding into some selected region of your boundary. Yeah, this is up to this assumption that all AME states are stabilizer states, or at least can be easily turned into stabilizer states. And this is just a toy model, which, that's all. Thank you.
Before you had a loop with only red dots on it.
Mm-hmm.
This figure here doesn't show that. No, just keep that figure, please. That is a wonderful figure. Then say that the Y1 there in the bottom left was a red dot.
This one?
No, bottom left.
Bottom left, uh-huh.
Yeah, the one below it, the gray, just exactly.
Uh-huh.
Let's say that there was a red dot and then the legs are coming out of it. Then how would this operate?
That the red dot was here.
Yeah.
Yes. So I define red dots.
Let's say that there was one and you are trying to do that.
Mm-hmm.
I mean, how is the transfer of the operator
Yeah.
to the network then when you have a closed loop?
Yeah. So then I would have some additional legs that would be going here outside, and then it will be my free-to-free code, because I have like 3 incoming legs. And if I will find my Y operator coming here from this leg, then it will have some associated Y logical operator on the outer 3 legs, and this Y will be like concatenated. This local Y will be encoded as in the logical form that is defined by the state. Mm-hmm.
Is a generic state an AME state? Like if I take a random, power random state, is that?
No, probably no, because it's hard to find them in a general setting. So there's in fact there's a library of AME states online. It's I don't remember the address, but it was made by Felix Huber from Siegen University, and then they have a table of local dimension D and number of qubits, and boxes they have colors green, then it means that the AME state exists, and then they have references to the papers that were introduced, and there are a lot of boxes that are blue and state AME state does not exist, and also some boxes that we are not sure if the AME state exists.
So it's small measure, like
yes, it seems so. Mm-hmm. Mm-hmm.
So these are somehow also equivalent to like N0, like N over 2 plus 1 codes or something, right?
Yes. So.
And there's some tables excluding those. So.
Yes. So this is the construction that's. But it's not like all AME states are associated with this classical code constructions. So only.
Quantum code constructions too, obviously.
And quantum code construction, yes, but in this form of AME state, this is the. So here, in general, you admit for d to the power of m words in this superposition. But the minimal number of words that is allowed for the state to be absolutely maximally entangled is just d to the power m half, like half of m. And then states that have this number of terms in the decomposition, they are connected with this quantum minimal distance codes.
That's cool.
Uh-huh.
That's not all.
And also you can, in this case, you can show that all of them, they are stabilizer AME states generally, up to the phase that can differ arbitrary, but they all lead to stabilizer AME states as a class.
So could you see this as you've found commuting local Hamiltonians for the sort of bulk of these holographic codes?
Mm-hmm. Yes, yes, yes. So by the construction, all of logical operators that are mapped to the boundary, that they commute with each other. Mm-hmm. Yes.
So do you get, there may be some kind of way to study these as models that have anyons or something like this, or is it just like excitations in the bulk using violated stabilizers, or is that meaningful? I think people have been searching for a while for Hamiltonians to describe these codes.
Mm-hmm.
It's interesting.
Yeah, maybe. I don't know. I was not thinking about it.
Do you get special problems out of the codes if you restrict yourself to planar graphs?
No, there should not be any effect. I was not checking different geometries, but it doesn't look like it should affect properties. Yes.
Do you know of a code that can only be derived from a non-planar graph?
No.
Okay, if there are no more questions, then let's think how again.
Okay.